All right, we're going to spend a bit of time today talking about the introduction to chemistry. So we're going to take a look at chemistry overall, and we're going to take a closer look at atoms specifically. So here we have our periodic table of elements, which we're going to address throughout this little piece. And let's just get started. So the first thing is that matter. Right, what is matter? We know we're surrounded by lots of different things. We're breathing different things. You're sitting on something, perhaps a chair, sitting at a table. Matter is any material that takes up space. So anything that takes up space, anything from, like I said, the chair that you're sitting on, which is very solid to us, all the way to the food that you eat, to the air that you're breathing, or any other gases around us. So any material that takes up space. Now that has gone into a bit further, and scientists have taken a look at that and said, okay, what are the different types of matter? And if we take something, let's say a piece of bread, and we break it down into its parts, maybe if you've made bread before, you know there's flour in there, there's perhaps salt in there, maybe a little bit of oil in there, water, flour. So all of these different parts go into making bread, for example. Then scientists took that bread and they wanted to break it down further and further and further to get to the thing that can't be broken down anymore. They did that, so if we take out the water, we take out the salt, we take out the flour, we separate it into its parts, and we break those down further. Let's say we get down to one of our biological molecules we'll talk about, which is carbohydrates. When we look at carbohydrates are also made up of different parts. So they saw the carbon in there, they saw the hydrogen in there, they saw some oxygen in there. And then they broke that down further, and they broke it down into what we call elements. And so elements are pure substances that cannot be broken down by chemical means into any other substance. They can't be broken down any further. So our elements are pure substances. So cannot be broken down any further. And then what they did was they took a look at these different elements, and then they put them in this handy little periodic table that we can see right here. This whole thing, of course. And all of this is the periodic table of elements. And they've been organized by various characteristics that we're going to take a look at. So these are all of the different atoms. Many of them are needed for life, which is why we're addressing this in our biology class. And so we're going to take a closer look at some of these, some of the main ones. And I can mark some of the main ones right now. Our number one that we're going to take a look at is carbon. So carbon is a major player in life. It's the backbone of many of our molecules, which we'll talk about. So carbon is a big player. Another one over here on the left side is hydrogen. So you should be familiar with carbon, hydrogen. The next most important one is actually oxygen, back over here by carbon, so oxygen. Then, next up, these are kind of in order of importance: carbon, hydrogen, oxygen, then nitrogen. So these are the four that are most important to life, and the ones that we'll be talking about a lot. The next one up, which we will be talking about a fair amount, is then phosphorus. And phosphorus is kind of down in here. All right, so those are the ones we're going to be talking about a lot. But first what we're going to do is we're going to look generally at the atom. We'll revisit our periodic table of elements, but the atom is our smallest bit of matter. It's where we're taking, remember we said matter is any material that takes up space. And then we talked about the elements, so we broke down, say a piece of bread, for example, down into its parts. And we said, okay, if we take carbon, we can't break down carbon into anything else. Like it's still carbon. It's not carbon and this. It's not carbon and that. Carbon is the element that it's been broken down into, one of the smallest parts. Then if we take carbon, for example, and we break that down and we look at what carbon looks like in its smallest pieces, then that's when we're talking about an atom. So let's take a look at an atom. So an atom, again, let's write that up here. An atom is our smallest bit of matter. And this is what makes up an element. So each one of those elements, the carbon, the hydrogen, the oxygen, nitrogen, phosphorus, etc., all of those are made up of atoms. They're made up of carbon atoms or nitrogen atoms or oxygen atoms. So the atom itself, we have this kind of central piece here, which is called the nucleus. And then we have what's around the nucleus. I'm just going to draw it kind of like this. And this is our electron cloud. So it's the basic structure of our atom. So if we look a little bit closer, our nucleus is actually composed of two different smaller pieces. So it contains our protons, which have a positive charge, and contain our neutrons. And neutrons have a neutral charge, hence the name there. So protons are positive, neutrons or neutral. So they are not charged, or they have no charge. We can indicate these. Usually we use this kind of cursive lowercase p with a plus for a proton. We use a cursive n with a 0 for a neutron. And then these are the two different pieces that make up our nucleus, which is in the middle here. So we can think of it as these little tiny circles, our protons and our neutrons, our positive and our neutrally charged pieces there. Then out here we have our electron cloud. These are electrons that are flying around this nucleus at a very fast speed. And the electrons are usually indicated by an E with a negative because our electrons are negatively charged. So our electrons are floating outside of the nucleus. If we take a little bit of a closer look at what's going on here, again, we have our protons, and the protons are really important in that they give us our identity. So this is the identity of the atom. So the number of protons, let me put that there, the number of protons actually tell us which element it is. So for example, if we're talking about carbon, carbon has 6 protons. Anytime that we see an atom, anytime that something is broken down into its smallest part, its atom, and they can see the protons, if they count 6 protons, then that means that that is carbon, that element. So the number of protons in the atom actually equals what we call as the atomic number. So 6 protons always equals carbon. 2 protons, for example, always equals helium. 1 proton always equals hydrogen. So the number of protons is going to give us the identity, or is going to tell us what type of atom it is. And so then changing the number of protons then is going to change the type of element it is. And when I say atomic number, again, that's giving us what the identity is. But if you recall, if we look at our periodic table, I'll kind of scroll back over there for a moment. If we look at our periodic table, I'll just use up here the hydrogen, you can see this little box. And in this little box, there's the number, and the number for hydrogen is 1. And that is our atomic number. So that's telling us number 1 is hydrogen, and that means it has 1 proton in its nucleus. Also, and we'll talk about this in a moment, but that also means that if it is a stable atom, then it also has 1 electron in that electron cloud. We'll revisit that in a moment, but if we look over here, again at carbon, we can see carbon has a 6, and we know that it's carbon because it has 6 protons, and that number there is our atomic number. So that is what I was kind of drawing down here with this little box here. Is we usually have our big letter in here, and then up at the top we have our atomic number, which in this case for carbon is 6. And then of course this right here is our symbol representing that element. So up here, this is our atomic number. Oftentimes also, and we don't need to talk about this too much for the purposes of this class, but then the number that you see down here at the bottom, I don't have that on the periodic table I chose for this, but in this case, if you see this, then the number at the bottom is called the atomic mass, which is actually the number of protons plus the number of neutrons. So protons plus neutrons equals the atomic mass. We're not going to use that so much in this class. There's our little mention of it, but basically we're going to focus on our number of electrons. So let's talk about why the electrons are important. So we have our protons and our neutrons. So again, let's just kind of draw. We have our nucleus here. I guess I'm just going to kind of draw like this because we're going to pretend there's certain numbers in here. So our nucleus, which has our protons and our neutrons. So remember, the protons are positively charged. Our neutrons have no charge. They're neutral. And then flying around there, we have our electrons. So oftentimes seen looking something like this with these kind of things floating around here. We have our electrons. And remember, our electrons have a negative charge. So the weight, I just mentioned the atomic mass. Mass is the weight of an atom, mass of an atom, atomic mass, is based off of our protons and neutrons. So protons plus neutrons equals the atomic mass. And this is because electrons have very, very little mass, especially compared to our protons and our neutrons. So our electrons are what we're going to take a look at when we're talking about chemical bonding. So these are kind of the important pieces here. There are isotopes. Isotopes are different numbers of neutrons in the nucleus, but for this class, we're not going to be looking too much at isotopes. So let's focus on our protons, understanding that our protons are what give us the identity of our atom. Understanding that the number of protons then in a neutral atom or a stable atom, our protons equal our electrons. So if we're talking about carbon, for example, we have 6 protons, recall. Then that means in a stable carbon atom, we have 6 electrons. Now what we're going to see is that our electrons move around a lot. And that's because rather than this drawing here, which kind of shows just these random circles around the nucleus, electrons are actually in what are called orbitals. And the way those work is that we have different levels of orbitals. So if we look at the different levels, let's say we have our nucleus here in the center. So we'll just kind of put an N here for nucleus, a capital N, not to be confused with our lowercase n, which designates neutrons. So we have our nucleus here. Then what we have is we have this first orbital. And the orbital, again, is where the electrons are going to be flying around the nucleus in. So they stay at certain orbitals kind of naturally, but then different things will move them to different orbitals. We're not going to talk too much about that. That's more in the chemistry arena. But we are going to talk about the orbitals to understand chemical bonding. So we have our orbitals, also called shells or electron shells. So we have our nucleus in the middle here. Then we have our first electron shell. Our first electron shell can hold up to 2 electrons. So our first shell, we can have 2 electrons in that shell. Our atoms, they want to have full orbitals. So the idea is that as all of these atoms or elements are interacting in the world, what they're doing is they're attempting to fill their orbitals so that they can be more stable. And so our first orbital here has a maximum of 2. Once it reaches 2 electrons, then that is a full orbital. It can't fit any more electrons in that orbital. Then as we move out, we have our second orbital, or our second shell. And then in our second shell, we actually can see that we have a maximum of 8. Okay, so we're going to have 8 in this case. I like to do, we'll do 2 here, 2 here, 2 here, and 2 here. So our first shell, or first orbital, has a maximum number of 2 electrons. Our second orbital has a maximum of 8 electrons. Then we'll go up to our third shell, our third orbital, and then in our third orbital, we also like to have 8 electrons. So 1, 2, 3, 4, 5, 6, 7, 8. So our third shell, we like to have 8 electrons. And I think that we'll go up to our third shell for now. So we have our nucleus here at the center. Remember our nucleus. And what was in our nucleus? Right, protons plus neutrons. And then we have our electrons out here. And remember now that we've talked about orbitals. They're in their different shells. Our first shell, or first orbital, has a maximum of 2 electrons. Our second and third has a maximum of 8 electrons. And remember, they're trying to be stable. They want to have full orbitals. So as they are interacting in our world, as all these atoms are rolling around, maybe not rolling so much, but moving around, interacting, they want to try to fill up those shells. So we're moving back over to the periodic table here for just a moment because I want to mention this desire, which of course atoms don't have, but we can pretend they have this desire to fill up their shells. This is what they're doing. So the reason that I brought us over to the periodic table of elements again is because this column here, all the way on the right side of the periodic table, these are called the noble gases. Noble gases. And the reason they're called the noble gases is because they have a stable number of electrons. So all of these guys over here in this column that is blue on this periodic table, these are the noble gases and they are stable, which means that they don't interact. So they have completely full orbitals. And since they have completely full orbitals, they have no reason to interact with anything else. They're not going to take electrons or give electrons to any other atom. So, for example, helium, which is one of the ones maybe you're familiar with, it is a noble gas. It's not interacting with anything else. We don't have a molecule that is composed of something and helium, unless maybe we force it or something like that. But naturally, normally, those guys aren't going to be interacting. The rest of the periodic table, however, is going to be interacting at various levels. So when we talk about them interacting, then we're going to talk about, again, going back to these orbitals. And that's why we have interactions, is because, remember, they have various orbitals, and in these orbitals, they want them to be filled up with electrons. So let's take a moment and look at, let's say, carbon. So carbon, our best example, how many protons does it have? 6, right? So we have 6 protons, which means we have how many electrons? Right, 6 electrons. So if we draw our carbon atom, right, so in the middle here we have our 6 protons, and then flying around it we have our 6 electrons. So let's put those in their orbitals. So our first orbital, how many electrons does it have in it? It has 2, because not only do we have a maximum of 2 electrons in our first orbital, or our first shell, our orbitals, or our shells, fill up from closest to the nucleus as they're moving out. So if an atom has more than 2 electrons, then our first orbital will be filled. So we have our 2 electrons here. Then that must mean we move up to our next orbital, our next shell. So we have 1, 2 already accounted for. So then we have 3, 4, 5, 6. So that makes up our 6 electrons. So if you recall, remember our first one, our first shell has 2, and in this case we do have 2. So that orbital, that shell is happy. It's got its maximum of 2. It's not going to be interacting with anything. Now our second shell, the one out here that we just filled up, has 4. How many does it want? Right, it wants to have 8, which means that we are missing 4 electrons, which means that carbon is going to be out there in the world interacting with other atoms, trying to get all of these electrons filled in. And so that's exactly what we see. What we actually see is oftentimes carbon is going to interact with 4 other atoms so that it can borrow its electrons. And we're going to talk about that specifically in our chemical bonding lecture. So let's take one more example. Let's take sodium, for example, because sodium is something we will talk about a lot as well. Na, which is sodium. So sodium actually has 11 protons, and if it has 11 protons, then that tells us it has, right, 11 electrons as well. So we'll put our little nucleus here, which are 11 protons, and of course there's neutrons in there as well, but 11 protons in our first shell. So our first shell has how many electrons? Right, 2. Because we have more than 2, it's going to fill up those 2 first. So then we're going to go into our next one. So we have 1, 2 in the first, then we have 3, 4, 5, 6, 7, 8, 9, 10. So we're up to 10 electrons at this point. We need to get 11, which means that we need to have a new orbital, right? Because this orbital is now full. We have our total of 8, our 1, 2, 3, 4, 5, 6, 7, 8 electrons in our second one, and that's the most it can hold. Since it's the most it can hold, then that must mean that in order to get to our 11 electrons that our sodium atom has, we're going to need to add another orbital. So if we're going to add another orbital, let me get rid of this here, and we're going to add our next orbital, our next shell. So we're already at 10, which means we just need to add one more. So there's one more lonely electron hanging out in our third orbital, or third shell. All right, so in this case, then we're missing lots of electrons, right? So we've got 1 here, we're missing 1, 2 here, 1, 2, 1, 2. All right, so in this case, we have our third shell. We want it to have 8 electrons. What it currently has is 1 electron. So what we'll see then is that sodium is going to be interacting with its environment, interacting with other atoms, trying to either fill these 7 electron spaces that are missing, or it will give up its 1 electron. And then if it gives that to someone else, then we're left with our stable second shell.